Hey everyone, and welcome to today's Explainer. Today, we're gonna unpack something absolutely fascinating. We are looking at a 19th century equation that secretly powers our entire modern world. It's kind of like an invisible engine that dictates exactly how energy and matter interact on the most fundamental levels. Honestly, understanding this is like getting the cheat codes to physical chemistry.
So I want you to think about this for a second. What do the massive Haber-Bosch fertilizer process, the intricate folding of biological proteins, and cutting-edge solid-state hydrogen fuel cells all have in common? On the surface, they seem completely unrelated, right? But the crazy thing is, human survival, complex biology, and our green tech future are all linked by one incredibly elegant thermodynamic formula, the Hoff Equation.
Okay, let's dive into this. Here is our roadmap for today. We'll start with the equation connecting the world, break down thermodynamics and chemical equilibrium, and then look at the geometry of the Van 't Hoff plot. After that, we'll explore complex systems, the optimization of industry, and finally, the future hydrogen energy revolution. Section 1. The equation connecting the world. To really set the stage here, we actually have to travel way back to 1884. That's when a brilliant Dutch chemist named Jacobus Henricus van Hoff published a monumental piece of work that gave us this exact equation. You can think of it like a mathematical translator. It perfectly translates the macroscopic, big-picture world of heat exchange down into the microscopic world of molecular bonds. Now, you might already be familiar with Le Chatelier's principle. You know, the rule that tells us which direction a reaction will shift when it's stressed out. But the Van Hoff equation goes so much farther than that. It actually quantifies exactly how chemical equilibrium shifts as temperature changes, giving us the precise heat budget of a whole molecular system.
Section 2. Thermodynamics and chemical equilibrium.
Now, what's really interesting here is how Gibbs free energy essentially drives the entire game. When delta G is negative, your equilibrium constant, K, is greater than 1. This basically means the forward reaction is spontaneous. It just wants to happen, creating a huge abundance of products. When it's positive, well, the reaction gets stubborn. It needs external energy to be pushed forward. And at exactly 0, you hit perfect, complete balance. But remember, this only tells us what happens at a single static temperature.
So, how do we track this across changing temperatures? Well, it requires a pretty brilliant logical derivation. Step 1. Gibbs free energy links the total heat, which is enthalpy, and the system's overall disorder, or entropy. Step 2. The Gibbs-Helmholtz equation steps in to determine how that free energy actually changes as the temperature fluctuates. And step 3, by combining these concepts, the pure differential Van 't Hoff equation is officially born. Now don't worry, we're not going to get trapped in the heavy calculus today. The absolute crucial takeaway here is that this formula translates those abstract, theoretical variables into real-world, highly predictable actions.
Section 3. Geometry of the Van 't Hoff plot. So let's translate all that heavy, intimidating math into incredibly simple geometry. Enter the Van 't Hoff plot. By placing the inverse of temperature on the x-axis and the natural log of our equilibrium constant on the y-axis, all that complicated calculus magically transforms into a basic straight line. And reading this simple straight line allows us to instantly, visually extract the hidden thermodynamic secrets of pretty much any chemical reaction. We all know every straight line has a slope and a y-intercept, right? Well, here, the physical shape of the data points hands us two distinct physical reality. The slope represents the enthalpy. It gives us the heat budget, immediately telling us whether the reaction is absorbing or releasing heat. The y-intercept, on the other hand, represents the entropy, what I like to call the chaos factor. It shows us the change in the system's disorder, or exactly how molecules are structurally rearranging themselves. And this brilliantly illustrates just how powerful this plot really is. Let's compare the two. For exothermic reactions, where heat is being released into the environment, the plot shows an uphill climb from left to right as temperature decreases. But for endothermic reactions, where heat literally must be absorbed to move forward, the plot shows a downhill slope. The geometric elegance here is instant. You can read the fundamental nature of a chemical reaction just by glancing at which direction the slope is pointing.
Section 4. Complex systems and nonlinear thermodynamics.
But as you probably know, science is rarely just perfectly straight lines. When we leave the highly controlled lab and enter the messy reality of nature, a system's heat capacity actually changes with temperature, a concept known as Kirchhoff's law.
So when you introduce extreme temperature shifts or highly complex biology, those nice linear assumptions break down, and our perfectly straight Van Hoff plot begins to actually bend and curve. For instance, biochemists see these curved plots all the time when tracking the thermal unfolding of complex proteins, like the TRVP3 temperature receptor inside our own bodies. The changing slope maps exactly how the protein structure warps in real time. It even applies on a massive macro scale, like the Clausius-Clapeyron equation predicting exactly when atmospheric water vapor is going to condense into rain clouds.
Section 5. Optimization of Industry and Life. Now, applying this theoretical lens directly to massive industrial chemical engineering, we find the von Hoff equation pushed to its absolute breaking point in the Haber-Bosch process. This is the process that synthesizes the ammonia used in basically all global fertilizers. But engineers face a seriously suspenseful dilemma here. Synthesizing ammonia is highly exothermic. So, according to von Hoff, to maximize your thermodynamic yield, you want freezing cold temperatures. But there's a huge catch: kinetics. To actually break the incredibly stubborn triple bond of nitrogen gas, you need blistering, boiling heat.
So how in the world do you solve a paradox where you literally need it to be freezing cold and boiling hot at the exact same time? Well, you use a clever closed-loop engineering compromise. Engineers heat the reactor way up to between 300 and 500 degrees Celsius under massive pressure. They just accept a brutally low initial yield of maybe 10 to 20%. Then they cool that resulting mixture all the way down to minus 20 degrees Celsius to condense and extract the liquid ammonia, and finally they infinitely recycle the leftover gas back into the system. They are literally feeding billions of people today by outsmarting the Van Hoff equation.
Section 6. Future Hydrogen Energy Revolution. For our grand finale, let's look at how this exact 19th century math is actively screening the green energy tech of tomorrow. We all know a massive hurdle in green energy is storing hydrogen. Instead of using bulky, high-pressure tanks, scientists are trying to store hydrogen gas directly inside solid metal lattices, creating what are called metal hydrides. But thermodynamically speaking, cramming a free-floating gas into a tiny solid box causes a massive loss of entropy. It's a total thermodynamic nightmare. To compensate for this incredible loss of disorder, the reaction absolutely must be strongly exothermic. Engineers map all of this out using the Van Hoff plot in what are called PCT curves, determining the exact heat needed to absorb and release the fuel.
But of course, they run into what's known as the hysteresis problem. Basically, some of these metal hydrides become way too stable. Once the hydrogen gets inside, it requires hundreds of degrees of heat just to force the hydrogen back out again, and that completely ruins the energy efficiency of the entire fuel cell. To fix this, engineers don't just use pure metals anymore. They literally physically destabilize the compounds by mixing multiple different alloys together.
And here is the incredible result. By creating a multi-alloy mix of lithium borohydride and magnesium hydride, scientists tracked the Van Hoff plots and watched the desorption enthalpy barrier completely crash. It dropped from a stubborn 67 kilojoules per mole down to an incredible 25 kilojoules per mole. That is massive. This single, simple mathematical plot guided them directly to a usable low-heat hydrogen battery compound.
Which leaves us with this really provocative thought. If a 19th century equation from a Dutch chemist can map the heat of a single unfolding protein, solve the paradox of global agriculture, and unlock next-generation solid-state hydrogen batteries, what other hidden thermodynamic engines are just waiting out there to solve our greatest global challenges? The blueprint of the universe is written right into these equations, and I really hope this explainer leaves you eager to dive even deeper into the beautiful world of physical chemistry. Thanks so much for learning with me today.